Cool. So I assume you can see my slides, and so far we've discussed a bunch of stuff about linear models, about gradient descent. You've seen some code. Now we're jumping into slightly more complex models. You've already studied that, you apply weights and biases and produce some output from some input. Now, what neural networks are doing is applying weights and biases stepwise and producing an output from an input. And we'll see exactly what these stepwise things mean. And we'll start with the simplest case of this perceptron that is simply, again, a single step of applying a weight and some bias to the input data set. I should get into some logistics before getting into the details of the lecture. So this is what we're going to study today. It's my cursor. I hate it when that happens. Yeah, okay, cursor is back. Cool. Before that, we should get into some two logistical things. One is, please, already mentioned this, posted about this, but please run your project ideas by us at the earliest, so we can give you substantial feedback and you can update your project ideas accordingly. We've seen two cases happening. One, you're biting off too much to accomplish in the next 4 to 5 weeks, and two, you're unclear about how much to bite off, in which case you're just not able to decide what the scope of the project should be. The great part about both of these things is the ideas that people are coming up with are very doable. Um, the challenge is carving out a tangible problem statement out of those ideas. So for that reason, talk to us, come prepared with these 4 questions that you should answer when you're chalking out a research project. You've already posted about that. Most of you know about that already. So I won't get into that, but just that's announcement one. Announcement two, we understand that the readings are getting a bit monotonic, I would say, like sitting and reading a page and then making a presentation about that is fine for 2-3 weeks, but it gets annoying after a while. So we did come up with this alternative where we will have the first 5 to 10 minutes of the class dedicated to 2 presentations, based on any of the 2 people in the class willing to talk about 1 or 2 of the research papers that they've reviewed. Ideally, just one research paper, 3 or 4 slides, talk about what's the literature, what's the problem what's the problem they're solving, what's the literature like in that area, what are they doing that's different, and the cool thing about their method and the results. So mini presentation to the class about what you studied and relating to the project that you're doing. So it's not like we don't have a limitation on what kinds of papers you can present. Ideally, keep those papers somewhat pick a paper that people will understand, as opposed to a super mathematical paper that you will have to spend a lot of time explaining. So in that sense, we'll open it up to volunteers if there are any in the next 2 days. Otherwise, by Monday, we'll randomly select 2 people from different groups to present one paper each on what project are we doing, and this paper ties into our project, and this is what we were reading, and this is what this paper is trying to do. So you'll have this recording so you can go back and refer to exactly what kind of things should be mentioned on the slides. Cool. Can I do polling on that? Interesting. Let's see. Would you prefer? Ay. Sorry, you can't see my screen, but I'm just trying to create a poll to check what the opinion in the class is like. I think this should be anonymous. I really also don't care about identifying people. It's just about trying to get a sense of what people would prefer. Um, Poll is live, so you should be able to post your answers, and it's anonymous, so I can't see who voted for what. Okay, 10 more seconds and then I'll close it out. And we're good to go. Okay, so I don't know if you can see the results, but I can share my screen. Desktop 2. So this is the result of the polling. About 32% saying readings and 68% saying research presentations.
Something
Yeah,
Discord is open. Mhm.
that's,
Discord.
I mean, it's announcements, so I
Okay.
figured it's fine. Yeah. So yeah, the maybe the easier option is for those of you who want to go for the readings route, you can do that. If we select you for the presentations, let us know that you want to do readings instead, and we'll select someone else. I assume that's a fair approach to this, so we're not imposing anything on you. And now we can go back to the slides for today. Okay, so we have seen that there are these points that we want to classify, and we've seen linear models, which is essentially drawing a line or a curve through the space in order to divide these points based on the classes. Now I'm going to talk about the same decision boundary, but in the context of learning with neural networks, or to be specific, perceptrons. So the perceptron, this is a very old picture from the 1960s. So to be clear, all of these ideas were 1950s, 60s, 70s, 80s. It's just that no one implemented them at scale and in a manner that was accessible to the public. So today you and I can build neural networks in the cloud, but back then, this is what one perceptron, set of perceptrons used to look like. Um, So we've seen this before, but I'll go over it again. I really don't like losing my cursor. We've seen this before. This output is equal to some function of weights times x plus bias. We've said that w times x plus bias. So this bracket represents an inner product. W transpose X, we've said this tries to approximate Y. Those are your predictions. And applying a sigmoid or a non-linearity on top of it. We discussed this in the softmax regression that, oh, we were converting our predictions into a probability now. Similarly, there are other non-linearities that can be also thresholded. So sigmoid of X can then be 1 or 0. If you're doing binary classification, you can apply a threshold on top of it saying, oh, if this is above 0.5, I'm just going to treat it as 1. If it's below 0.5, I'm going to treat it as 0. That turns into a class probability. So different, we've already seen all of these. So there's first is binary classification, then you have scalar real valued for regression. So you can predict Y from X. And then there are probabilities for logistic regression where you don't threshold it, but you treat it as a value between 0 and 1, and therefore it becomes a probability of the class. If there are any questions, I'm breezing through this because this is fairly straightforward and we've covered most of the pieces necessary for this. But if there are any questions at any point, please feel free to stop me and we can discuss. Now going back to this other problem that you discussed. So suppose you have to classify spam from ham or non-spam. Can someone tell me which or what is the decision boundary that you would prefer to draw between these two things for a good classifier? You can name the color in the chat. I have the chat. Do have the chat. So we have two greens, no blacks, one black, one purple, no red, another green. Okay, so it seems like the consensus is towards green, and Joseph added an explanation here which says it looks like it has the best separation in my opinion, which is fair. So if again I don't know why the cursor keeps going away, but I guess this is how life works. So the green has like generally decent separation. So maybe I should explain the other way around. So if you look at red is super close to green here and super close to red here. So the point being, if this red moves a little bit over, then the red boundary will not be able to classify it well. Don't understand at all why this happens. With green, with black, again, it's close to red and close to green. Purple is super close to red, not close to green. Slight imbalance there. Whereas green is like roughly equidistant from the closest greens and the closest reds and maximizes that distance. So that's essentially, it's the margin between the closest red and the decision boundary, or the closest green and the decision boundary. So this is a maximum margin classifier. That's what they call it. The English term just means it maximizes the separation from both classes. So that's intuitively why people seem to think green is a better classifier, and in fact, it does turn out to be better in this case. So the way I would arrive at this green decision boundary is via the perceptron learning algorithm, which is saying step one, it's saying let's start with zero weights and biases, then repeat for each yi in your data set. If the product of your yi and your prediction, this w, the bracket w times x plus b is just your predicted y, and this is your target y. If the product of both is less than or equal to 0, then you're doing something wrong. Then you need to update your weights. So your weight goes from your original weight, w goes to w plus yi times xi, and b goes to b plus yi. Why are we? How do we know that if this is the condition for it to be negatively classified, for it to be wrongly classified? Could someone explain this to me? To repeat the question, why does this matter? Why does this product being less than 0 imply that it's negatively classified? It's wrongly classified. Okay, I'll get to your question in a second, Gaurang. If anyone wants to unmute and answer, that's also completely fine. Because this is a basic decision rule to classify. Okay, I buy that, but tell me more about this. What is this yi?
So if we classify it wrong, but like if it's plus, if we classify it as +1 and if it's actually -1, then the product will be negative. But if we classify both, like if we predict it +1 and if it's actually +1, then the entire product will be +1, and if it's -1 and -1, the product still remains as +1. So if it's negative, then we have actually classified it as wrong, and if it's positive, we have classified it as right one.
This is exactly the correct explanation. Thank you. I didn't see who unmuted, but thank you. So I will first. I should answer the. I should complete this explanation. So what um, whoever just said was, if it's the same class, if it's the predicted class and the target class is the same. Remember that right now we're talking about a binary classification, so you can consider +1 -1. If +1 is classified as +1, then the product of this predicted y and true y will be +1. If +1 is classified as -1, then the product of this true y and the predicted y is -1. Similarly, if -1 is classified as +1, this is wrong. That means the product will be negative. But if -1 is classified as -1, then the product will be positive. So we saw 4 cases. 2 of them are correctly classified. Product is positive because minus minus is plus, plus plus is plus. I'm talking about the product here. And both the other cases where plus is classified as minus or minus is classified as plus, the product will be negative. So that's all that this mathematical term is saying. That's that the target times the prediction will be less than 0. Then you have to update your weights by a certain value. And end after all of them are classified correctly. This is similar to your stochastic gradient descent, with the loss considered as the maximum of 0 or the negative of y times your prediction. And to go back to a question, is the class value 0 or 1 or its y coordinate in R2? Is yi the class value or its y coordinate in R2? I believe it's the class value because you're using your x's to predict your y's. Cool. So let me go back one slide to answer the question asked before this. There was a question that said, in this specific application, should we not aim to reducing false positives? Which is why I said purple. Erring on the safer side, basically. Yes, you're erring on the safer side for green, but for red, you're not erring on the safer side. For red, you're actually doing much worse than you could have been doing. So when you say maximum margin classifiers, you want to maximize the margin to all classes. You don't want to maximize the margin to one of the classes and minimize the margin to the other classes. And this ties into a very, very important point. And I'll raise this again this is section 4a of this talk. There will be section 4b, but I'll raise this in the context of bias and fairness, about how you have to be fair to all classes, because a lot of times you run into challenges with algorithms that don't treat everything fairly. So anyway, that's not the only explanation there, but that's one of the explanations. Let us move to what I want to talk about. For cats and dogs, as an example, like this is how you're trying to classify them. The minute you start getting new examples, you update your classifier. So you see the black line shifting a little bit to account for these differences. And essentially that's how you want to go about. That's what you're doing with this perceptron learning algorithm, that you start somewhere, and I'm asking you to focus on the black line and the slope. Change the slope when you see more examples, change the slope when you see more examples, change the slope when you see more examples, until all of these examples are correctly classified. So essentially what you're doing is you're trying to maximize this margin or this radius R enclosing the data. The margin row separating the classes. And the way you're doing this is you consider this domain of the data, and you say within this domain, if I see data points here, this is how I'm going to draw my line to classify them. And that's what you want. You want your predicted y times, again, my cursor. Really don't know what's going on. your predicted y x transpose w plus b times your target should be greater than equal to 0 in order for the margin to be maximized. And you want this, well, based on the margin, you can calculate how far you are from it. Cool. And from, and I should add a caveat of, for most data sets, for data sets that are linearly separable, it is guaranteed that the perceptron will converge after r square plus 1 by rho square steps, where r is this radius enclosing the data. I don't think I'm going to get into the proof for this, but if you have a question about this, then we can discuss that during the office hours. Cool. However, and now, well, this is Smola telling us about this interesting story about a game development lab that created this AI that used the perceptron learning algorithm. So they said, okay, well, humans exhibit certain sets of actions, and we want to see if we can use this to build an in-game AI. And this was long, long ago. So in-game AIs were not the were cool, like were very rare to have and a cool feature at the time. So they built this god character where you could either train your god to be a benevolent god and take care of the villagers, or you could train your god to be a destructive god and destroy the villages, and the villagers would have to fight back. So those sorts of things. So you could do one of two things, and they assume that humans will behave in a certain way, and the god will learn from these actions that the humans take and behave accordingly. And so this was the assumption that they made, but no one really checked if this assumption was true. So when humans tried to play the game, well, when they released the game and humans actually ended up playing the game, turns out human behavior was super inconsistent. So some days humans behaved benevolently, other days they behaved destructively. And so the learning algorithm could not converge because there was such an inconsistency with the data. And because of that, the game got progressively harder and harder to play. And ultimately, it just didn't work. The objective function for the perceptron is similar to that of the SVM. Can you please point out the difference between the two? This is a great question, and this is actually covered in one of Smola's videos as well. So the point of the SVM is to find a projection of the data in a space such that you can shatter those points, in the sense classify them. So drawing a line through these points is called shattering them, if you successfully classify all of them. Point of the perceptron learning algorithm is to draw this line such that it shatters the points without having projections of the points in some space. I wasn't pointing my cursor anywhere, but yeah, it's disappeared again. I was just moving my hands around. That's why. So perceptron shatters the points. SVM finds projections of the points such that they are then separable. Fair? Cool. Yeah, we can also cover SVMs in more detail in the office hours. I feel like I oversimplified a lot of things, but I think this is fair to say. Cool. So the perceptron, the challenge with the perceptron is it cannot learn an XOR function. And this is a very popular problem you'll see in a lot of, it's just mentioned there, the XOR problem. So what is this XOR problem? Well, if anyone can tell me what line could classify these or could separate these examples or shatter this data, let's say shatter this data, I would be very obliged. So can you draw a line that divides the green classes from that separates the green classes from the red classes? One answer is, I think, only if you added extra dimensions, by which, oh, my iPad is here. Thanks. Let's see. Sorry, I'm just joining with my iPad. I'm still waiting for an answer if someone has an idea of how to shatter these points. Cool. Use a combination of and, not and, or perceptron. That's an interesting idea. So what? Oh, I clicked on the slides. Okay. So what Jagrut just said was, let's consider two separate classifiers. So I'll get back to Joseph's point, but first let's consider two separate classifiers. The yellow classifies two examples. The blue also classifies two of the examples. And if you combine the two, and I absolutely hate this. Don't understand what's going on. Cool. If you combine the two, you're going to have this situation where you have, oh, I see that I'm on the wrong screen. And my cursor disappears again. Give me 1 second. Resume call. So the good news is I may have figured out my cursor issues, and we can resume where we stood before this. Cool. So we're talking about learning the XOR, and we said, so some chat message. Okay, Jerry is an important point about, and I'll read it out for the benefit of the recording. I think in perceptron, convergence is not guaranteed, which means that it can run forever. You can't always get the optimal hyperplane, whereas in SVM, if a hyperplane exists, then it will give you the optimal hyperplane with maximum margin. SVM would also stop if convergence is not possible, whereas perceptron may run forever. So I caveated when I mentioned like the perceptron converges, I said for linearly separable data sets. So in that case, I don't know if these are two entirely different things, but we can get back to it after the lecture. So sorry, I don't have a clear answer for you right now. That's on me. I don't want to say something wrong with confidence. Okay, so we discussed using two of these lines together in order to separate the points. The yellow line tells us that the green and 1 and 2 lie on the positive side and 3 and 4 lie on the negative side. Cool. The blue line tells us that 1 and 3 lie on the positive side and 2 and 4 lie on the negative side. And when we combine these two, that's when we get this ultimate idea of XOR, separating XOR data. Yeah. Okay, so combining the two, we end up with the correct classification, but this makes it clear that the perceptron is really not going to be able to learn this because the perceptron cannot, like, by itself, a single perceptron cannot create two decision boundaries and combine them. So naturally, in order to do this, we have to create two separate perceptrons and combine the predictions of both of these in a way in order to obtain the gray one. So your black is your input goes to both perceptrons, blue and yellow. And then finally, we combine the outputs of both perceptrons into our final gray prediction. Not going to spend a lot more time on that, but this is the general idea. Like if you generalize this notion of two perceptrons to more perceptrons, now you have data. Now you have more complex data that you can separate, which is super cool because then you might think, well, if I have more and more and more complicated data, does that mean I add more and more and more perceptrons? Well, it seems like that's what people have done until they reach some sort of limitation. And then they're like, okay, maybe we need to innovate more on the algorithms and the architectures and these nuances in these architectures. But in the beginning, the idea was just, yes, let's add more perceptrons, more layers, more depth, and try to create more complicated models. Again, I will get back to this point when I talk about model capacity. So the more perceptrons you add, now you can see that the model capacity increases. What does model capacity mean? The ability to shatter more complex data. So draw a line separating even more complex data than we've seen here. So that's, it'll come up again, so I'm mentioning it here. But this now motivates, now you know where these neural networks come from, why. So there's a question, what exactly do you mean by shattering data points? Great question. I mentioned this very briefly earlier, so maybe it's time to draw a diagram. If I have data points x and y, well, I should name them x and y. It's class 1, class 2. Shattering them just refers to drawing this line that divides them. So if you're thinking of like a big pizza, with several different toppings on the slices in independent slices, then the shattering means cutting that pizza into different pieces. So dividing the drawing a boundary that divides them into separate classes correctly. That is what I mean by shatter. Not in, like, every single point has to be correctly classified. There is no approximation here. There is no probabilistic modeling here. There is just draw the line, divide everything correctly. So and I'll explain why I'm talking about this terminology of shatter. It does not account for misclassifications. There is no misclassification in shattering. Otherwise, you're not shattering. Otherwise, you're trying to do some probabilistic calculation. So yeah. Now, the general idea that we drew here, mathematically expressed, is this, right? So it's this, at the hidden layer H, you get your input X times W1, whatever is your first weight matrix, plus B1. So W times X plus B, as usual, is our prediction for the Y. Then you pass this prediction through a nonlinearity. Then you pass this output. So this, then you pass this H, which is the prediction times the nonlinearity, into, you don't pass it, sorry, you multiply it by another matrix of weights and add another bias in order to obtain the output. So input, prediction, multiply, prediction, output. Yeah. And you can imagine you can keep doing this. So input to prediction, prediction to new prediction, prediction to new prediction, and that's how neural networks work. And the final prediction is taken as your output. And at each layer, typically you multiply it with a non-linearity. Can someone tell me why we multiply it with a non-linearity? You can guess. You don't have to know. One of the answers is to bound the outcome. Otherwise, it would be a simple linear regression problem, because otherwise it can just be compressed to a single layer. Most of this is the right intuition. So yes, you're absolutely right that if you don't do that, then you're essentially reducing it to a linear layer. But you can actually be doing worse than that, because if your input is multi-dimensional and your layer width for the hidden layer is much smaller, then you're not just doing a linear mapping, you're doing a linear reduction. And then you're mapping it back to the output, which could be high dimensional. So you're saying, I'm compressing this and then trying to expand it again, which means you might be losing data in the process if you're just doing a linear mapping. Fair? Sorry, I should have mentioned I paused for questions if there are any. Okay, I'm going to assume not, and you seem to have the right intuition covered, so good for that. Is there an advantage to compressing the features? Yes, excellent question. There is actually an entire class of models. Well, forget models. Dimensionality reduction is a big, big, big thing, right? So there are advantages to compressing it, but there are certain ways in which you want to compress it. You don't want to just drop half the data. That's also a compression, but that's a very lossy compression. So I won't get into a lot of detail, but you can think of it as like, if I have an image, then your computer is compressing it. When you upload it to Facebook or Google Drive or whatever, there is some sort of compression algorithm being applied so that they can store petabytes of data. So this is a useful idea. It's just that you don't want to apply it in a mindless way. So yeah, don't like dropping half the data or just taking products of data that result in a lower dimensional space without those weights meaning anything. Cool. Or yeah, you're taking a linear transform, right? We've studied this, I believe. Matrix multiplications as a linear transform. So you want your linear transform to sort of discover some underlying pattern that is lower dimensional so that you capture that pattern and you are able to reconstruct the data from just that pattern. Cool. I'm going into too much detail now, but hopefully this gives you a good idea. And in fact, even for neural networks, this idea of variational autoencoders came about by saying, okay, there is high dimensional data, but it lies on some low dimensional space. So we want to discover this low dimensional space and then check if we can reconstruct the high dimensional data. That is all I will say. Before moving on, how are we doing on time? 8:39. Okay, about halfway through. Cool. So speaking of these activation functions, these non-linear activation functions, one of the things that we have sort of seen before, but I will reiterate, we've seen this in the softmax regression, the sigmoid function that we pop on top of our outputs to convert the outputs, the real valued outputs, into a probability. The sigmoid function looks exactly like the graph depicts here. Can someone tell me what might be one of the issues if you apply the sigmoid and then you want to calculate some sort of loss of the output and then go back and update the input? I see that you've done your readings. So vanishing gradients is the right answer. I'm sorry, I want to wait longer for more answers. The idea is just that around this part and around this part, your gradient is essentially zero. Why do I know this? Because if I draw tangents here, the tangents are straight. So the straight line indicates the slope is zero. Well, straight line parallel to x-axis indicates the slope is zero, which means that at these points or for very large values, you're going to get almost zero gradients. So you're going to have problems coming back to smaller values of your weights. I think that's all I want to say about that. And so you have a problem with the sigmoid, and so people came up with better ideas that, oh wait, can we use this one instead? And that seems to suffer from similar issues. And this took years, by the way. Like I think it was at least like a 2-year gap between just using the sigmoid and then finding something called the ReLU, which is the rectified linear unit. But now you see that this slope is non-zero. I'm not drawing. This slope is non-zero. So for whatever x values, there will be some gradient and it will bring you back towards where you want to go. However, the same challenge occurs here because the slope is zero. So typically what some people do, or at least what came about after that was, well, what if we just take this as a smaller slope, but this is now a learnable parameter alpha, where alpha is the slope of the negative slope, where you want this to still come back to zero. So that is called the ReLU. Forget what the P stands for. Okay, so your now clear on activations, what sorts of activations we want, why we want them. We've gone from like, here is some data, here is like a linear model. We studied that before. Now we're like, okay, here is a perceptron. This can also do learning. Multi-layer perceptron, combining multiple perceptrons in order to shatter the data. We've talked a little bit about SVMs, but I'll expand on that if time permits at the end of the lecture. And we've now spoken about, okay, so in this multi-layer perceptron, in order to do effective learning, firstly, we want to ensure there's a non-linearity. Secondly, we want to ensure that that non-linearity has some gradient at whatever point the weight is at. Now I'm going to talk about multi-class classification. So before this, did we not? I mean, we've been looking at the same diagram. So O1, O2, O3 could correspond to 3 different classes. And the way you do multi-class classification is you do, this is probability of, I should write it as probability of class equal to 1 is equal to 0.3. Probability of C2 is equal to, sorry, 0.5. Probability of C3 is equal to 0.7. And so you're just going to say that, oh, I'm going to take the max of this vector 357 should. And there I have my multi-class classification. I should say argmax because it's the argument that we're taking, this class 3, not the value. Remember the difference between argmax and max. But that's about it. Nothing more there. Yeah, we've talked about this. Take the softmax of the outputs and then consider the highest predicted probability. So I don't think I want to say anything more about that. We have right. So now just visually, let me clear this. You can think about adding more and more and more hidden layers, and ultimately, like, you want to get to this size, right? The output layer is depends on the number of classes. If I have 2 classes, then I should have 2 outputs. So the intuition is you want to slowly start compressing your data. If you're going from like a higher number of inputs to a smaller number of outputs, then you want to slowly start. You don't just want to dump everything in one layer. And this has to do with the idea of capacity. So you want to increase the capacity of the model to capture the patterns in your data. And just having 2 output neurons here directly would not enable you to do that. So that's why you add multiple layers and you slowly go from an increased width to a decreased width. And in a hand wavy sense, there's also the idea that, if you allow a neural network to have more capacity, then it will learn by itself what are the right things that it wants to store when you reduce its capacity, instead of you just directly going to a smaller capacity. So yeah, how do you decide the width of a layer? No particular answer for that. Like, it's up to you. It's almost entirely arbitrary. People have shown, like, there is a lot of study now on this idea of, and I'll get to parameterization and over parameterize and all of that. So I guess I shouldn't get into that right now. Cool. Let me clear this. So far we have spoken about the perceptron, the multi-layer perceptron, the learning algorithm, why we need nonlinearity. We don't know what sort of architecture works, so architecture searches are needed, but we know that we can compose layer upon layer. And that's it for that section of the presentation. I'll give you a 5-minute break, after which I will get back and talk about some really cool stuff that has to do with, well, I can show you the slides. That has to do with model selection, weight decay, and dropout, particularly giving you some intuitions about the problems we run into and why we came up with these ideas of like weight decay and dropout and how to select the right models. So 5-minute break. Let me pause recording. I'll be around if you want to ask questions. So a couple of updates. I have successfully Googled SVMs and perceptrons, and it seems that my intuition was reasonably spot on. I shouldn't say reasonably spot on, but anyway, the intuition was correct that the vanilla perceptron, it deals with linearly separable data and it finds the boundary that classifies these. If there is no such boundary, then this vanilla perceptron will fail. That's why we came up with the multi-layer perceptron, right? The multi-layer perceptron will now try to find the correct boundary that separates this data. But again, with the perceptron learning algorithm, if this data is not linearly separable, there will be challenges. For the SVM, it essentially is the same idea that there is some data. You want to find a boundary that separates this data. Linearly separable data case, pretty straightforward. It can find the boundary of the hyperplane that shatters this data. The problem with the perceptrons, where if this data is not linearly separable, doesn't occur in SVMs, because then it tries to find a soft margin where, okay, some of it is incorrect, but there is still some optimal boundary that exists with minimum misclassification. And so it finds that boundary. But overall, the high level idea you want to take away is just that the SVM projects these points into some space where it becomes more shatterable than it was before. And now I'm not talking about like shattering in the perfectly classified sense. Now I'm talking about soft margins, where soft is just an indication of probabilistic, where some misclassifications may be allowed. Another point of difference comes between, at least this is what the intuition is, the perceptron works in an online update fashion where you see point after point and update your boundaries. The SVM takes all the data and calculates this optimal boundary. It doesn't work in an online fashion, although this was the initial version of SVMs. There have been versions after where they have come up with algorithms that operate in a stochastic manner. I don't have comments about that. This is what I read and I'm trying to convey to you in a simpler fashion. You should find easy answers on Stack Overflow to go through, but at least I hope I covered this intuition of what this SVM is doing, what the perceptron is doing, and then they come slowly closer together as you consider more recent algorithms to train SVMs, and multi-layer perceptrons and L2 regularized perceptrons is super similar to what the SVM is doing. And I'll talk about L2 regularization in this lecture itself, but I didn't want to bring it up because I haven't gone through it yet. But yeah, hopefully you are fair to have this question, like you are right in having this question that, well, if perceptron is doing this, what is the difference from an SVM? I've hopefully covered some of the points, and you can read more about it and get back to me. So with that said, and if there are no more questions, we can get started. Deep did mention in chat that regarding the prelude, instead of that, you could also have a leaky ReLU with a fixed alpha value of 0.01 or something similar. The general idea being you want to avoid this issue of vanishing gradients, and sort of get to a point where your weights converge to optimal values. Cool. So now we can get into the, in my opinion, slightly more interesting.
Swapnil, there was, I think, a question on chat. You told that you will answer that.
Yeah, great question. So will the number of features a neural network uses not be reduced unless the width of one of the layers is reduced? In general, I would say yes, because as long as you have, let's break down the question a little bit. Number of features a neural network uses is the input going to all of these perceptrons and those perceptrons going further. So yes, if you have a very, very wide network, then your input is going to a very wide hidden layer. That hidden layer is going further and you're using all of that data. So in that sense, you're not reducing the use of features. So what people came up with, and I'll explain, this is again has to do with the later part of the lecture, this idea of dropout, saying, well, we don't want to fit too much to our training data, because that then what you're then doing is you're memorizing the training data. So you're saying, if these are my homeworks, I solved too many homeworks, I just end up memorizing these homework problems. And then if I see even something remotely similar in my exam, I just write down the answer that I memorized instead of actually trying to solve it. Right? So you don't want to overfit to your training data. And we'll cover that in this part of the lecture. But I was giving you, I was basically getting at, there are different ways of avoiding using too many features, or that's not the technically correct way of saying it, like the number of features it uses. I should, I don't know the correct way of saying that, but hopefully the intuition is clear, and we can formalize the terminology later. So suppose, getting back to what we're talking about, suppose we have this problem where you are hired to investigate who will repay their loans and who will not, right? You're given complete files on a bunch of applicants, and you find that 5 of these applicants defaulted within the 3 years that this data extends for, or this loan was extended for. All 5 people, as it turns out, wore blue shirts during their loan interviews. And so if you dump this data into your model, then the model is clearly going to learn that, oh, this was the common feature between these 5 people. And I don't care about the rest of the features. This is super important because this has a direct correlation with whether they defaulted or not. The model doesn't realize that blue shirts are a really bad signal, because that could have just been a random choice that day that the people made. And so the question is, how do you create evaluation techniques that go beyond, like step beyond just prediction accuracy, and look at really what the model is learning and what the model is doing? And this effect, this blue shirt effect, is not just as like, it seems really trivial that, oh, blue shirt, so you can just ignore that and you can figure that out. But really, when you go to real world applications, this has a lot of impact on communities that are marginalized. So for models that and there are some really nice diagrams in this section. So what happens is, no one intends to create these biases, but also people don't sit and check what their model is doing. They don't sit and check why their model is doing that, to be more precise. And they don't sit and check, like, okay, are there any biases in my data that I should be aware of in advance? And a lot of times that just happens because we don't really know what we're doing, because we just dump everything into neural networks, and because we get cool predictive accuracies, we're like, hey, this works. But the point is, like, model evaluation needs to go beyond just predictive accuracy, and that's where all of this interpretability stuff comes in. That's where all of these new versions of data sets are being released, where, celebrity data sets had a lot of Caucasian and white and male faces, and you need to add more women, you need to add more people of color, and increase representation. So that's so someone said this very famous statement, I think Georgie P. Box, I don't remember. All models are bad models, but some models are useful, right? What does this mean? Well, you cannot use a model to describe the world. The world is far more complex than a model can describe, but sometimes these models do useful things for you. So that's what it is conveying. And I don't know if the corresponding statement for signals in your data, signals are noise. All signals are bad signals, but some signals are useful. Seems to me that's the right thing to say. But getting back to, there's this presentation by Jennifer Wortman Vaughan at the NYU AI school that had this nice diagram, which basically combines a lot of, it's like this landscape of, these are the biases that are super popular that happened in real life. For instance, Google Photos did classify black faces as gorillas. This is a real thing. This had a lot of uproar. But you can imagine that even at Google scale, these biases can and do creep in. Amazon did have a recognition, resume filtering system that just threw out resumes from women, because the historical data showed that they had biases against recruiting women. So when you use this data to train an algorithm, it is clear that your biases are going to be reflected and almost always amplified, which is like ridiculous when you think about the outcome, but no one sat and studied this. And when people did, they realized, oh crap, we messed up. I'll pause if there are any questions. Maybe I should pause after the next slides. George EP box. Yeah, all models are wrong, but some models are useful. Cool. I should pause after the next slide. So essentially what this is saying in terms of what we just studied, right? So Maurice Hart had this really nice plot where it said, well, a majority of the data that we have on the left, and now my cursor is visible, I'm so grateful, is correctly classified. But the minorities are who are disproportionately affected by this line being drawn, um, um, are going to suffer. So we really need to think harder about what sort of boundaries we want to draw when we have data from minorities that conflicts with what the data from the majorities is saying. So that's hopefully gives you a super clear idea of what we're doing wrong or what goes wrong often in these cases and what we don't think about. Like if you look at the data as a whole, you're going to say, oh, some points are misclassified. That's fine. I have a 2% margin of error. That's perfectly okay. But no, those 2% fall into the same class, and that class is disproportionately going to be affected. And that's important to think about before you go about deploying these models into production. But anyway, going back to what we were talking about, model evaluation. There are different ways of evaluating your model. And one of these ways, I'm going to now start with my usual example from at least my life. I was an IIT aspirant, did not do well, but ended up doing okay in life. So going back to like thinking about these traumatic days from my childhood, I'm going to ask you, how did IIT coaching class prepare us? By us, I'm hopeful that there are some others in this audience that share my childhood pain. Um, I think just what I'm getting at is they had a set of exams, right? So when you're evaluating a certain student's performance, you typically just use exams. And it's a whole different story that exams don't measure everything. But in this case, they measure a performance of how you're going to do on your final IIT JEE exam, which is like this final test equivalent to your SATs or whatever to get into universities, which in this case is one of the IITs. For context, the IITs are one of the the premier institution for STEM education in India. Probably, I don't know non-STEM, but yeah, the engineering colleges equivalent of MIT, Harvard, Stanford, whatever. And I want to get into an IIT, so I'm going to solve these problems. And these problems are divided into various stages, right? So first we have homework problems, which are like thousands of problems over the 2 years that you study for them. Then you have like a next stage of exams is preliminary tests, or you might even take test series from other coaching institutes. And then finally you have your one final exam that everyone appears for after having trained for so long. And I'm going to use this to motivate the same thing. The way you train your model is almost exactly the same as IIT coaching class prepares you for the IIT exam. How is this the same thing? Well, in for homework problems, we have lots of different problems, right? For when you go to the preliminary tests, you have fewer problems, but you have these specific these some might overlap with your homework problems, but there are a lot of new problems now. And again, like test series at other institutes, a lot of repeated problems, but also a lot of new problems. So it's in a sense testing how well you know your homeworks and how well you can do on some new data. And the final exam is almost always completely unique problems, none of which you have seen before, but they're still problems using the same concepts that you have learned, right? And this maps almost one to one with the idea of training, validation, and test sets. So your training set is lots of homework problems that you're solving. Your validation set is some of these drawn from homework problems, some sort of new problems. In a way, you're just like you're double checking that you really do know what your homework concepts are, and you're preparing for some sort of test, in the sense that there are some new problems. And finally, for your exam or your test set, so we covered training, validation. Now with test set, completely new problems. You have never seen these problems before most of the time. They draw on the same concepts, but they're very different problems. And that's exactly what and so the idea of training error and generalization error have to do with the same ideas as training set, like performance on training and validation set, and performance on test set. So I'll go the slide quickly. Training error is model error on the training data. Generalization error is model error on new data. We've already been through an example, but just to give you an idea of what we are trying to avoid, we're trying to avoid this performance that student A, I should, it's easier. We're trying to avoid the case that student A is getting good marks just by rote learning the homework problems. That's why the IIT JEE exam does not have similar problems to homework problems, because then you're not really testing for learning of a concept. You're just testing memorization ability. And memorization or overfitting is a big problem for neural networks, which I'll get into in 2 slides. What we do want, though, is this, where you want to get the answers, you want to get marks for giving the correct reasons behind answers. So yeah, so that's what I want to say about this slide. And I'll just read through this line. Doing well on past exams or training error does not guarantee a good score in the future exam, generalization error. Because like we said, your model may be learning, may be predicting well, but it does not necessarily mean it knows the concept. So this is the converse of that. Like, just because it does well on homeworks does not mean it has learned the concepts and therefore will do well on prediction. How do you ensure that it has learned the concepts? A super hard question to answer. But in one thing we can do is create these validation sets and check which model is doing well on these validation sets. So that's where the validation idea lies. Between training and test, you create these practice exams and give yourself these practice exams, or give your model these practice exams to check that it does well on all of these practice exams, and that increases your confidence of saying it has probably learned the right concepts and it is like student B. It's not just memorizing like student A. Cool. Now I can scroll through some slides. One way of creating a validation set is just create different subsets of training data. So if this is my training data, I'll say that, okay, I'll keep 2 of them as training points, and I'll use my third point for validation. And there is this idea of k-fold cross validation, which says, okay, this is one validation set. Now you can use these 2 points for training data and create a new validation set, which has to do with this point. And remember that you're training all these models separately, right? What you are testing for is the capacity of your model. So your model is a student, right? You give the student different sets of homework problems and practice tests, homework problems and practice tests. You don't learn continuously, but you learn separately just to check your students' abilities. Hopefully this is clear about why I can create these 2 entirely different training setups and check if performance on all of these setups is okay. That's the goal. Like, can the student learn in setup 1? Yes. Can the student learn in setup 2? Yes. Another way of creating a training set is using this as your training and the middle one as your validation. So you can imagine you can do this in many different ways. If you have multiple data points, you create one sample. It's subsampling basically. Your population is now your training data. You subsample to create some training set and some validation set. And finally, your test set is completely separate. You do not play around with your test set. That is a one-time thing. You evaluate on the test set when you're finally sure about this is my model, this is now what I want to test, and then you go back and test. Why can you not evaluate multiple times on test set? That was a question. I'll pause for answers. The evaluation will be biased. That's correct, because that's using the test set as cross validation. You can no longer generalize. Perfect. Both of these answers are spot on. You cannot look at your exam questions, go back, and then study your homework again. That is the idea. Your exam questions are exam questions. You will give that exam once in your lifetime, and that's it. So yeah, not going to hop on that point more. You seem to already follow it. This was the algorithm that I was discussing. This is called k-fold cross-validation, where this 1, 2, dot, 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 k. You can create k different subsets for validation, and then the rest is training data. And then you can play around with that and train your model on each of them separately, because you want to test the model or the student's abilities, nothing else. Cool. Now let's get to this part about underfitting and overfitting. So I mentioned this before, and I'm pretty sure most of you are already familiar with this, but I want to get to an important point that states over like to explain parameterization, like why do we care about the number of weights and biases in the model? What do we mean about more? What do we mean when people say over parameterized neural networks? Like this model is too complex for this data. People say all of these things, but like you need to have this mathematical intuition of why this might overfit or why this might underfit. And so I think we're good on time, so I can afford to tell you about this new sport I'm creating, which is called Cricut. And this is a version of cricket, with the only difference being I have now a variable number of players. So it is not fixed. I can create an IPL team. IPL is just an Indian Premier League. It's a version of cricket that lasts for 20 overs, or like a fixed set of balls are bowled and whatever. That's not relevant here. I am assuming some familiarity with the game of cricket. There is a certain batsman. Batsman hits the ball. Ball goes over the boundary. Batsman scores some runs. There are some fielders. Fielders catch the ball, throw it back. I mean, look up cricket if you're confused about cricket. But my point is, I'm creating a game called Cricut, which now has a variable number of players. So same, the rest of the game is the same. The idea is the same: score more runs and get the other team out before they score enough runs to actually win the game. And my question now is, okay, I should erase this. My question now is, how can I win at Cricut? And I've given you the batsman, I've told you that, this is the general area where this batsman is likely to hit the ball. And I've given you some players to start with. Remember that the difference is now you can have a variable number of players. So how do I win at Cricut? Any ideas? I will give you a hint. The number of players is not fixed. I said I've given you some, but that's not necessarily all the players you have. Okay, I got a message saying, could you repeat the question? I didn't get it. I'm saying there is a batsman. He's going to score some runs. The question I'm asking is, how can I win, or how can I increase my probability of winning the game of Cricut? In regular cricket, you have a fixed number of 11 players. In Cricut, you don't. And the goal is I have to stop the batsman from scoring a lot of runs, right? Because I want to do that, and then I want to score enough runs. So simplest strategy for how to win at the game of Cricut. One of the answers is have fielders everywhere. Batsmen hit over the boundaries, sure, but their batsmen can also hit over the boundaries. I can't control that. I see a hand raised, so I will pause for a second and ask Devang to unmute. Is there a question, Devang? You're not audible if you're saying something. You are unmuted though. Okay, I'm going to assume no question exists. This is perfect. Like the point is just, and maybe I'm sorry if I wasn't too clear, but the point is just have fielders everywhere. I said you have a variable number of fielders. The game is to stop the batsman from scoring enough runs, and so increase the chances of you scoring a lot of runs. Gotcha. And so I can just keep adding players, keep adding players, keep adding players until I cover the entire field with players, and the batsman can no longer hit a ball anywhere without a fielder getting to it. Is everyone with me so far? Is there a question? I'll pause for 30 seconds just to sanity check that this seems obvious to most people. A simple yes will do if you followed what I'm saying. Cool. In that case, so let's say I add a lot of fielders. Can someone point, and this is again IPL style, right? So there is a certain auction and you have to pay money for players. So can someone tell me the problems associated with adding a large number of players? One of the problems is logistics. One of the other clear problems is paying them all money. There is a certain cost to adding an infinite number of fielders onto the pitch. And another slightly less obvious cost is that these fielders are not necessarily going to behave optimally, right? There is going to be some collisions on field. Like if the ball goes off and people are running towards the ball, they tend to not really field well. And especially with like hundreds of people on the pitch, this is going to be a problem, right? Yeah, I mean, someone pinged me saying allow the crowd to come in and field. Yes, if I do, the crowd might like stop the ball, but there's going to be so much confusion that they're not going to be end up, then it's not ideal for the entire crowd to feel like they might perform better if only some of them come out and field. So the point I'm trying to get at is this is exactly like a machine learning problem where your problem is to figure out, if I know there is some data which is this brown lines where the batsman is going to hit, I want to fit my model parameters such that they align with this brown line and they can predict something along those lines. That's again a very hand wavy explanation. These fielders are now my parameters for the model, and I can tweak these around to create an optimal fielding arrangement or arrive at the optimal values of these parameters to make my predictions. And in general, the more the number of parameters I add, the better my model is going to do. But the challenge with more parameters is this collision, and this collision is essentially like overfitting. It's going to be too specific to where the model is predicting. So if the batsman, for example, hits the ball along this line, I have no fielders here. I have just overfit to my training data, right? And even if I start, I'm not going to, okay, let's not get into that. But that was the point I was trying to drive home, that, you know, the more fielder, the more parameters you add for the same amount of training data, the more likely you are to overfit to this training data and therefore generalize poorly. Or when your test examples come in like that, you're really not going to do well. So hopefully like this clarifies what people mean by over parameterized models, and like especially with over parameterized neural networks and what they're doing. And yeah, it's not necessarily true that more parameters means better prediction all the time. Although in general, it is fair to say that the more fielders you have, yes, you're going to do better. But again, it has to be, you have to monitor like where to place these fielders. And this idea of like evenly spacing out fielders, or like monitoring how far a fielder can like move about in this radius of where they're fielding, that is something similar to regularization, where you're saying, okay, I'll allow my weights to move around, but within a certain finite bound. um Again, not exactly a one-to-one explanation, but hopefully it gives you the correct intuition for what model capacity is, and the data complexity is. So I'm sorry, I wasn't talking about data complexity yet. I'm going to start talking about it now. But just to be clear, like if it's a super simple data set, then a super low capacity model is pretty okay. Like it does okay. If it's a complex data set, then this low model capacity might not be okay. So it might underfit your data. However, if you increase the capacity of the model, then it works well. But if you have a super high capacity model for a super simple data set, then you're going to overfit and you're going to just memorize all your data. So overfitting, you'll typically see these kinds of plots where you'll see that the model is super complex in between the data points just because it can be. So I could just draw these two lines, both pass through the same data, but the blue model just has so many more parameters that it becomes more complex than the red model. The blue model could approximate the red model, whereas the red model can never approximate the blue model. But for this simple data set, we don't really need the blue. The red is working really well. And in fact, if there's a new point, if there's a new prediction to be made here, if there's a new prediction to be made here, then the red model is probably going to do better than this blue model. Anyway, I'm getting too much into detail, but you take away the general idea. So yeah, not going to spend too much time, but I will just repeat this point that high capacity model tend to memorize the data set, the training data set, which is bad because the test set might not be the same as the training data set. And so I should clear this. My bad. And so there is a certain optimum in terms of model complexity that you want to get to. And this scale is model complexity, where you have a low training loss, but also a low generalization error. So your test loss is also low. And it doesn't, the more complex you make the model after, it tends to start increasing the test loss. And the reason I wanted to drive home this point about model complexity and over parameterizations was, now that you have this intuition that, oh, like super complex models might not be the best idea all the time when I have simple data. Now I will break that intuition and tell you that sometimes, or it has been shown that super complex models, when you say this is the training, the test error, you will often see this, that, oh, test error is increasing, stop training. Well, it turns out if you keep training after that, and I should label the axes properly. So a lot of times in machine learning, people will tell you that if this is my error, no, sorry, this is my training epochs, just training time, and this is my loss. If I use red for my test loss, then what people are saying is, if you have a super complex model and you keep training, then your test loss will slowly start increasing. And even as your training loss keeps decreasing. So that's why they say that, if your model is very complex, this is overfitting, where your training loss is reducing. Sorry, your training loss is reducing, but your test loss is increasing. Well, it turns out that people showed, like, if you keep training after this, at some point your test loss again starts decreasing. And this is like very crazy. Like, why does this happen? What is going on here? And like, why did this suddenly come about? Well, someone had the the idea of continuously training and saying, well, let's see what happens. Like, if I keep training, what's going to change? Like, at this point, people claim that you are memorizing your data set, right? That your test error is so high, you cannot predict on new examples, but your training error is so low that you know all of your homework problems. So that's when you have memorized but not understood the concept. But no, as it turns out, after that there is another reduction and your test error goes down. And so this is called double descent, and you should look up double descent if you're interested in this phenomenon. But it's important to mention that, you know, people teach you in textbooks up to this point, and they say, oh, you know, you shouldn't overfit and all of that. But like, when people do research, they do tend to explore ideas beyond that. So you don't have to stop where the textbooks ask you to stop. You can step beyond that and try to explore some more concepts, and maybe it turns out you'll make the next big machine learning discovery. I would not recommend it for the course project though, because you don't know that you'll discover these things. It's better to stick with smaller doable projects before jumping into this kind of research. But hopefully it's clear why that was such a unique thing. If there are questions about double descent, I can take them after the class. Specifically the why question, I know that some people have tried to answer it. I still don't know the answer, but it's been discussed widely. So, and in general, over parameterized neural networks, that's the point I was getting at. Like, these complicated models that we spoke of, they might not be such a bad idea. That was what I was getting at. Okay, so we've already spoken about model capacity, or the number of fielders on the pitch that can capture the ball, or whatever the number of parameters. Typically, you compare two factors, the number of parameters and the values taken by each parameter. Why are the values important? Well, if all the fielders stand at the same spot, it's not really going to increase your model capacity. So the values that these parameters take also matters as a measure of model complexity. Not, yeah, I don't think I want to say anything more about that. Remember that weights are matrices, and so a weight that maps some input m to some output n will actually be a matrix with these many things. That's why this is t plus 1 times m plus 1 times k. This 1 corresponds to the bias term, bias at layer L and bias at layer L plus 1. Whatever, but just like, when you see such diagrams, always think of like, what are the basic things that we're talking about, and this must be a complex, must be a mathematical description of how many weights there are. Anyway, that is fair and fine. I should talk a bit about the VC dimension. So Vapnik and Chervonenkis were two super smart scientists who came up with this idea of shattering, and this is where this is the same shattering that I was talking about before. So they said that the VC dimension is the size of the smallest data set that is not shatterable by this model. So for the perceptron, we were talking about, it can shatter this linearly separable data, and a data set of 4 points that we spoke of, which lay like this. For the simple perceptron, where am I? This is non-separable by the perceptron, but it is separable by the multi-layer perceptron. So for the perceptron, the VC dimension, perceptron is equal to 3, because 3 is the maximum number of points, no matter how you arrange them, that the multi-layer, or that the simple perceptron can shatter. Or in another sense, the same thing, any way you arrange 3 points, the vanilla perceptron can separate them, but 4 points, now you need a multi-layer perceptron to draw some sort of decision boundary between them. So that's in general, this is the VC dimension for the multi-layer perceptron. This is super important for learning theory, but it's much harder to do for neural networks, again, because in general, it is hard to say like, this is exactly what a neural network is doing. If we knew that, then we can easily tie it back to, this is probably its VC dimension. But because we don't know exactly what neural networks are doing in terms of at every point, this is the weight that will update if you see this point, because the loss will go back. And so that's not easy to do, especially with hundreds and millions of neurons. So I think that ties in with the difficulty to compute the VC dimension. And there are a number of other reasons, in the sense that weights might not converge to their optimal values or whatever. But I don't know that. I'm just going to stick with what the slides say for a change. The bounds are too loose for neural networks, which means that this VC dimension is not really telling me anything, in the sense it's going to tell me I can't shatter a data set of 1,000,000 points, or something like that. Like, sure, but like I really can't even shatter 100,000 points. So the 1,000,000 point upper bound is super loose, given that my model has a much lower capacity, or vice versa. Lower bound might be too loose in either case. Here, though, it is the upper bound because it's the minimum number of points that it cannot shatter. So any more points than this in the data set, and your deep neural network cannot shatter this. But you never hear about that because that's not easy to tie down. Cool. We've already spoken about data complexity, but the way you measure this is just consider the number of examples, the number of elements in each example, the spatial or temporal structure of this data, and the diversity, like we spoke about the classes, the minorities and majorities, and those things. I don't want to say anything more about this. Yes, I should spend some time on weight decay and dropout now. So I mentioned L2 regularization before, and now I'll get to what I mean by that. Remember this diagram about like allowing your weights, like allowing a complex model versus simple model, and so on and so forth. Well, the way you can also force your complex model to be simple is to add this to your loss term. What is this? This is the norm of your weight. What you're saying is, I don't want my weight being too large. That's it. That's what you're saying. Like, don't make the norm of my weight too large, because large weights lead to these fluctuations. Like, even if you have a small change in data, you will have a large change in your output because of the weight. Oops. I should connect my charger. Okay, so that's the reason for adding this regularization term, is to ensure that your super complex model does not fluctuate wildly. Fluctuations are because of weights being very large and very small values of very large magnitudes. So in order to reduce the magnitude, what do you say? Well, you penalize large magnitudes. So you say, I'll add a magnitude term for this in the loss for this set of weights. So if the weights are a really large magnitude, my loss would be really large. And I'm forcing the model to not take large weights. That's basically it. Yeah, I don't think I want to say anything more about that. Mathematically, then you have your usual loss, but now you also have this regularization term, or we call it L2 regularization because this is the second norm of the weight, right? What is the lambda? The lambda is a certain hyperparameter that controls how much regularization you want to apply. Lambda is equal to 0, obviously negates this term, which means no regularization is applied. Lambda tends to infinity implies that this is a super, like you want to force weights to super small values if lambda is infinity, or like a really large value. That's what it implies. So then your weights will be super small and almost close to 0. So then you're not really doing any learning, I would argue, because your weight 0 just don't have any effect, or are useless. But yeah, that's this hyperparameter lambda. So hyperparameter is parameter that controls the values of other parameters, other tasks within the learning. Fairly straightforward. You still have your regular loss. Remember that this is just an additional term to that loss in order to compensate for more complicated models. Cool. So geometrically, what is happening is there is a certain space that the weights vary in. So this is like the if this is like the space that the weights vary in, you are forcing it to come closer to this unit circle around the zero. So if you remember, x square plus y square is equal to 1 was this unit circle around the x and y axis. This was the equation, or at least I think so. And w norm of w square is equal to 1 is essentially saying the same. So therefore it is like norm of w square are these unit circles of different radii based on what regularization you apply. Hopefully this is clear. That's what the plot is showing. And so the optimal w that satisfies this entire loss function is going to lie somewhere at the intersection of this norm. This function goes to 0 plus this function goes to 0. So two spaces, you want both to go to 0. So the intersection point is where like this goes to 0 and this goes to 0 intersect. I will pause for a second for those who want to ask me questions about this geometry stuff. Okay, if not, then I can move ahead. Yeah, this was just basic geometry, x squared plus y squared equal to 1. Some plane equal to 0, some circle equal to 0. Combine both of these solutions. That means you have regularized this and found the solution to that. So minima of that. And that gives us this update rule. Like if this is a new loss, then based again, you want to minimize this function. So you take the gradient with respect to the weights, because you want to minimize it with respect to weights, right? So gradient of the function with respect to weights and set it to 0. And that's exactly what the next slide is doing. Gradient of function with respect to weights and set it to 0, which gives you this gradient term. So the gradient of the second term is just lambda w, and we ignore this gradient of the loss for now because that will be the same for different problems. But this update rule then becomes I should mention I meant this will be different for different problems based on your choice of loss function. So that's just why we ignore that for now. But we do know that this lambda w squared term will be the same. Like you're using the same regularization for every problem. So the gradient of that regularization will be the same for every problem. So the update step then reduces to 1 minus some learning rate eta. I think so. So the learning rate eta times, like if this is your loss, x. Yeah, I think it's fairly straightforward. Like I don't know what I should say about any of the math here, but it reduces to 1 minus eta lambda. So this is some quantity less than equal to 1 times the original weight minus eta times your gradient of loss. Well, I shouldn't say gradient of loss because this entire thing is the loss function, right? It's the new loss function. So gradient of, I don't know what to call this term. But anyway, that is what your update rule reduces to. There is a question. How does norm of W square work for neural networks? Do we treat all weights as though they were one giant vector? Yes, to be specific, one giant matrix, because most of the weights, if you remember, or I can go back to the slides. Maybe they were not in the slide. Okay. Sorry, let me go back to the original slide. If you remember, escape. Where are we? I just want to go back to this because I didn't spend a lot of time on this, and so I should. Like this weight, this W, oh, clear this. This W is Rm cross N, and this W2 is Rm. So this is like the output layer. Only the output layer will be this, whereas all of the hidden layers will be a matrix. Because your X is Rn and your B is Rm. So W transpose X plus B should be a M cross N times R N cross 1 plus R M cross 1 equal to R M cross 1. I'm just doing a dimensionality analysis, so that's hopefully answers your question about taking the norm of these weights. Cool. W2 is RMA only if the number of output neurons is 1, right? I think so, because the output layer, wait, let me double check. W2 is RM only if the output number of output neurons is 1, right? No, I don't think so, because this results in, okay, let's, I should not. Oh, cool. Okay, got it back. So if my output is Rm cross 1, this implies that I have M outputs, M classes, probabilities. Does this help make it clearer? The output of this, yeah, cool. Okay, now we can go back to that slide. Where am I? What am I doing? Keynote, but the other keynote. Okay, back to our update rule. I'm sort of running low on time, but I think we should be good. The last part, and so this is called weight decay because this is less than 1. Like this 1 minus quantity is less than 1, and that is multiplied by the original weight. So you're decaying your weight because you're adding this L2 regularization term. That is clear. Let us move on to the next slide. So another way of regularizing, and this ties back to the question that was asked before, I think Gaurang asked about like what features are really used for learning. Well, we don't want to force like our over parameterized I should stay on this slide while I talk about that, right? So we don't want to force our over parameterized neural networks to memorize the data. We want to avoid the fact that our over parameterized neural networks might memorize the data. And we saw a couple of ways of doing that. We saw one, like force the weights to lower values. We saw, what else did we see in the fielder example? Just keep less fielders, space the fielders out. Another way of saying keep less fielders is like take some fielders off after every couple of overs, right? So that is the same thing as dropout, where you're saying, well, after some layers, like at every layer, I will drop out randomly, just zero out some of the activations, so some of the output. So essentially, I'll get back to the intuition, but what you're saying is with some probability, yikes, with some probability, some of the inputs are going to be zeroed out, right? This is, no, this is perturbation. I feel like this is different from what I wanted to explain. This is not the same, but my point was just zero out some of them randomly at each training step so that you don't overfit your training data, which exactly corresponded with this diagram, but I felt like there was math about that exact thing. It's not. Different ways of forcing your model to be robust. Now, what does robust mean? I mean that if I change my input by a little bit, I don't want that whole big curvy line. I want it to be the red, smoother line. I don't want this. I want this. So if I change my weights by a little bit, I don't want to jump up and down by like a crazy amount. I want to just remain close to my original prediction. And one way of doing that is to artificially just add noise to your model and force it to still predict the same way. So that is training with input noise, or Tikhonov regularization. Inject noises into internal layers. And the math that describes this is on the next slide, which is saying that I want to add expectation zero noise. So the expectation of the input is still the true value, but there is some sort of noise term that I would add otherwise, with a certain probability. Keeping it expectation zero, we have discussed this. I just mean like on average, I will add an equal noise above and below the value of the input. So I'm not going to spend a lot of time on that. But you should review expectation zero noise if you haven't. Yeah, this was what I was going for. Like you can also just drop out, in the sense like zero out certain input values. Like I can drop this neuron, and this neuron for going into my next layers. Like I can 0, 0, 0. And this turns out to give good results in practice. I don't, yeah, this dropout, you drop out H2 here. So I don't have an explanation for like why, other than I feel like dropout has been studied. So like explanations do exist. I just don't know like of the mathematically formal notation, more than saying like you are avoiding overfitting by not learning from too much of the training data. So that's the hand wavy explanation. I feel like there is a formal explanation for it. So you drop it out after you apply the sigmoid before you go to the next layer. So that's all I'm going to say, and we're actually at time. So I will just say one last thing. You don't want to drop out during inference. So during your test set prediction, you don't want to drop out randomly, because that means you're adding some bit of randomness in the predictions. It's not completely random because your weights are obviously fixed. But if you just pick arbitrary layers to drop out, then the next time you predict, you don't remember what was dropped out. So then you might have problems replicating your results. So typically dropout is frozen, like, or stopped for inference tasks, but it is done in training tasks, because in training you can do random stuff until you fix the weights. After you fix the weights, no more random stuff. Now you want deterministic results. And I think that's all there is to that. I'm going to pause for questions. We have 3 minutes. According to the paper, applying dropout to a neural network amounts to sampling a thinned layer from the main network. Yes, I forgot to raise this point. Essentially, what you are, essentially what you're doing by dropping out this node is creating a thinner layer during training. And so you're not as over parameterized as you would be with this node. And doing that to multiple layers and multiple nodes is really helpful.
Swapnil, I think the another intuition was like you want each neuron to be like expressive enough, like basically not as in two neurons basically jointly collaborate and like that way. So let's say if one neuron's prediction changes a bit, then another like leads to something different prediction. So you want the individual neurons also to be expressive enough, which is why you kind of like remove some neurons in a layer, and such that the entire neural network is still in like most expressive like that way. So that is also another reason or like intuition behind why dropout works. Like
Super
like trying to
important
reduce
point.
this joint collaboration.
Super important point. Thank you so much. You want to ensure that even without this guy, the other neurons are capable of making the right prediction, so that you're not excessively reliant on this dude for predicting whatever your output is. Um, I guess I don't think I can say it better than Jared. Thank you for bringing that up. Okay, if there are no questions, I can probably first stop recording.